So now, this video is dedicated to one of these students who asked me a very beautiful question in the comment section. He asked me, sir, whether we basically get confused in the depletion width. That depletion width, when depletion width will increase, when it will decrease, what was the reason for increment and decrement? All those doubt is going to clear in this video. Okay, I am going to start this lecture from scratch, but using my previous videos concept I'm going to use. Sir, this is the representation of two figures, and let me take these two figures for explaining this one. I will take this figure 1 and this figure number 2. Now this is the basically a semiconductor material. In the semiconductor material, suppose all over the material there are so many silicon atoms and there are so many covalent bond. Now I want to dope this region with pentavalent impurities, and adding impurities pentavalent create a region that is called N region. Similarly, in this region we will dope with boron, and they are trivalent impurities, and addition of boron result in P region, and with the addition of bond, what is extra in this region? So this is basically in these regions holes are extra, and in this region electrons are extra, and these things we know based on the previous videos. But other than that, all over the PN region there are covalent bond. When we dope this region with pentavalent and when we dope this region with a boron atom, what will happen? These holes, some of the holes from this region and some of the electron from this region which is near to the junction will involve in a deal, resulting in a region that is of negatively charged ions, and here we are positively charged ions, and this region is called the depletion region. And let me assume the depletion layer width is D. With the formation of these charged ions, there result a internal electric field EI. I represent for internal electric field. Now we know one formula. That means electric field is equal to V by D. If you remember from your 12th class 12th concept. So now I'm going to replace this electric field with the internal electric field. Now V built-in potential VB divided by the D, that is the thickness of the depletion region. Now this formula I will be using to explain each and every concept. Remember this formula, E is equal to V by D. So the internal electric field depends on D and VB, built-in potential, as well as in D. Now this depletion width depends upon so many factors. Now tell me, sir, in this scenario you have not drawn the charge carrier which is generated due to thermal energy. So now I'm going to draw those charge carrier also in the picture. So now let me draw those charge carrier also. Sir, here few minority carriers and few holes are generated. Other than that, we know one covalent bond again created 2 electrons, and here's hello. Now there are so many holes in this region, so many electrons in this region, minority electrons, minority hole. Now one person asked me this question, sir, this covalent bond, you have told me that here also covalent bond, here also covalent bond. Now this covalent bond which you are saying that weak covalent bond breaks due to thermal energy, there is a possibility that the covalent bond which are present in the depletion region will get broken due to thermal energy, but you have not shown any electron or hole in this region. Please tell me the reason for that. Sir, if in case due to thermal energy any covalent bond will break due to the internal electric field in the depletion region, if any covalent bond will break, so it will generate two electrons and two holes. But due to the presence of the internal electric field, these electrons will be moved to this side and the holes are moved to this side. So now, if in case by default some of the covalent bond in depletion region will get broken out, these electrons and hole will be separated as soon as they will be generated. So ideally in depletion region, whether covalent bond will break or not, they will be separated as soon as possible. So that is why you have not drawn any minority carrier concentration in the depletion region. And this depletion region will be free of the charge carrier, whatever be the condition, whether at 0 Kelvin, whether at thermal energy or 25 degrees centigrade temperature also. Now this picture is clear, sir. Correct? Now if you see this picture, sir, there is a possibility that we can dope this region with high number of boron atom, and we can dope this region also with high number of pentavalent impurities. What will happen? Now take this case in this region. Now I am going to increase the carrier concentration here. So now if the electron concentration will increase very high, and this is denoted by N plus, that is high concentration of pentavalent impurities, and the P plus denotes high concentration of boron. So if you are increasing the doping in this region, if you are increasing the concentration in this region, what will happen? If you increase this concentration to very high, what will happen? There will be very large amount of holes, and you know, if there is large amount of holes present over there and large amount of electron present over there, they will try to squeeze or try to come together each other, because large number of holes, they will try to move this side, and large number of electron due to diffusion, because there are large number of, because from large carrier concentration it will move to lower concentration. And because of this, what will happen? Because of this, whatever ions are present over there, first of all they will get squeezed due to the pressure from the hole this side and due to the electron or large number of electron from this side. So because of this, what will happen? The depletion width will get reduced. That means this D will get reduced as compared to this case. So that is why people will often say that when the doping concentration increase at their respective side, there is a possibility of reduction of depletion width. Not only there will be a reduction in the depletion width, but also there is a large number of probability that more number of holes and more number of electron from each other make a deal, and making a deal will indirectly will increase the internal electric field. So if we see the formula, internal electric field is equal to V by D, what will happen? Due to increase in the carrier concentration here and here, first of all the internal electric field is going to increase. Why? Because more and more holes and more electron will make a deal. Earlier, few at the junction will make a deal, they are free to move here and there, they are not interested in making deal. But if this area will become more and more concentrated, and this area also become more and more concentration, they will make a deal, and due to this the internal electric field will increase. So the internal electric field will increase. This will be the first effect. Simultaneously, this D region will get decreases because large number of force, both side force is applied. So this depletion layer will get squeezed, because these are the ions only. They will get a force from this side also and this side also, and ultimately they will squeezed. So ultimately this D will get reduced, and you know from the formula, if D will decrease further this electric field will increase. So now By seeing this condition, you must know, in this scenario, if ei is the internal electric field, but if you increase the concentration here, which is basically a case of Jenner diode, then D is getting reduced simultaneously. Because of this high doping, electric field is very, very high. Now let us assume this electric field is near about 1 kilovolt per meter. Let us assume very high, 1000 volt per meter. Here the internal electric field is normal. Let me assume 400 watt per meter, volt per meter is the internal electric field. Now tell me, in this case internal electric field is high, or in this case internal electric field is high? In this case internal electric field will be high. Why it is high? Not only because of the large deal happening between the holes and electron, because large number of holes and electron concentration, but also simultaneously this decrease in the depletion width also results in more increment in the internal electric field. Got it? So now this is the scenario, and this scenario is for that condition when we have not applied any external bias. Then internal electric field is, suppose, let us assume, I have assumed this rough data just to compare that in which electric field will be high. In this electric field will be high. Why it is high? You can see from this equation, from this expression you can elaborate, because more and more deal results in ei. Due to large concentration, the depletion width get reduces. So now people will say, when we dope p region and n region highly, then there is a decrease in the depletion width. Getting my point? This is point number one. But we have not applied any external bias. Now we will see, when we will apply external bias, what will happen. Now sir, we want to see the operation in the reverse bias case. So in the reverse bias case, we are going to apply the negative voltage or lower voltage to p type. So that means I am going to apply lower voltage to the p type and the higher voltage to the n side. So this will result in reverse bias, and I will do this by slowly increasing the voltage. Now if you see this case, now what will happen? This is high voltage, suppose this is 5 volt, and this is suppose 0 volt, or we can say that minus 5 volt. So now tell me, this is positive, this is negative. Now tell me, because of this positive charge carrier, here it is negative, an external electric field will exist. This is the direction of the external electric field. This is E external. An external electric field direction will be positive to negative. And see, this is the D for the, this is the D for the formula. This is the whole specimen thickness, and this is the E external field, and now this is the applied voltage. So if we write a formula, external voltage is equal to applied voltage, what we are applying, divided by the D, that is not, I'm not going to D with a, I will replace this with a, because D we have taken for the some depletion region, I will take capital D. So now this is D. D is not going to change, but as soon as you are increasing the applied voltage from 0, 1, 2, 3, 4, 5, what will happen? This is constant, because this is the specimen thickness, this is constant, but this is constant. So this external electric field will basically depends directly on the applied voltage. When we increase applied voltage, the external electric field will increase. Now see this situation. the external electric field and the internal electric field directions are same, so it will favors the internal, both will get added definitely. But tell me, this external electric field and this external field, they are basically in the same direction. Now what will happen, you will go on increasing the applied voltage, go on increasing the applied voltage. A time will come when the applied voltage gives sufficient amount of energy to this electron so that it will move fastly in this direction, and the holes are moving in this direction, and while moving, this electron have so much energy that it will collide with the covalent bond and it start breaking covalent bonds, and this will happen at a particular voltage we applied, and that voltage is called the avalanche breakdown voltage. Clear? Now what is the electric field? 400 volt per meter. Now this external electric field will increase this electric field, no doubt, because internal electric field, external electric field, both the magnitude will get added, and here the electric field concentration or electric field will get increased, but not very high. Up to it will go to 800 or 300 or 800 or 700, that much. For sudden rupturing of covalent bond, we want high volt electric field. This condition, although it is increasing the internal electric field to certain level, but this internal electric field is not enough to break all the covalent bond. But if anyhow this internal electric field is already high, then if you increase a little bit voltage, this electric field voltage will become near about 1300 or 1400. This 1300 or 1400 voltage or electric field is capable of breaking the covalent bond at sudden, and this is achieved in this condition because already electric field is very high. Here also electric field is there, but by applying the voltage, you are increasing voltage field. This is also increasing, but it is not able to increase this internal electric field to a value which allows sudden rupturing of covalent bond. But in this case, if you apply a reverse bias, then what will happen? The direction of the external field again is going to be the same. This external field definitely going to increase this internal electric field. That is why when this external field will increase this internal electric field, this internal field is already at value 1000 volt per meter. Now slight increase in this electric field will result in sudden rupturing of covalent bond in the depletion region. Why? Because in this depletion region, see, the external electric field is from here to here, but in this region, internal electric field plus external electric field is there. In this region will experience very high internal electric field. Although 1000 kilovolt per meter, further enhancement in the electric field is possible due to the reverse bias, and this result in very high electric field in this region, and so many covalent bond will break out, or sudden rupturing of covalent bond will take place in this region, and this result in Jenner breakdown condition. Clear? And now one more thing, people will say, when you reverse bias the junction, people will say the depletion width get increased. Why this is happening? I want to tell you that. See, this is plus and this is minus. All the holes which are previously due to diffusion, they want to move in this direction, but as soon as you apply a reverse bias, these holes will get attracted by this negative charge, and these electron will get attracted in this direction. As soon as you reverse bias this junction now, earlier both the holes and electron will try to move in this direction, and because of this these charge ions are getting squeezed, but now they are free, they will expand, and that is why people will say in the reverse bias condition this depletion width get increased. And you see this situation here also, same condition, this hole will get here and this electron will get that side, and because of this there will be a relaxed region D, and because of the relaxed region the charge ions or the anion and cations which are present, they are getting relaxed, and because of this relaxed region the depletion width increases, and that is why people will say in reverse bias depletion width increases. Why increases? You know why? Sudden rupturing of covalent bond in the Jenner breakdown, because already internal electric field is very high. As soon as you apply some small voltage now, then also this internal electric field will be capable enough or more than enough to break the all the covalent bond in this covalent depletion region. But in this scenario the internal electric field which is available was not very high. You, in order to get a sudden breakdown we need a minimum electric field, and this minimum electric field is not achieved by this configuration, and in this case only breakdown is possible because of the applied voltage, and this applied voltage is such that the electron, these minority carriers and here this electron are getting so much energy so that it is basically breaking the covalent bond one by one electron, 2, 4, 8 and 6, and this process will happen because of the high applied fold, and because of this V applied there is no enhancement in the electric field or very small amount of enhancement, and that electric field enhancement is not capable of breaking any covalent bond or sudden rupturing of covalent bond, and this is the difference between these two diode, and that is why this is called avalanche diode and this is called Jenner diode, and this is the basic difference. Here also in the reverse bias direction the E external will be in the same direction of E internal. In this case also the E external is in the direction of E internal, but together these two is not enough for sudden rupturing of covalent bond. But in this case these together at very small voltage is capable of enough to break sudden rupturing of covalent bond. And why this is capable enough? Because already due to this concentration variation or enhancement in the concentration we have achieved high electric field initially only, and this is very useful for voltage regulator circuit as compared to this one. We are using this, not this nowadays. There was certain reason for that. I will tell you when I will discuss the IV characteristics of Jenner diode and IV characteristics of the avalanche diode. Hope this doubt is clear now. When depletion width will increase, when we add impurity more and more, the depletion width will get reduced. But as soon as we will apply reverse bias, the depletion width will increase, but simultaneously in this case the electric field is initially very high, so as soon as you increase little bit voltage now, then also it will achieve that critical voltage or critical electric field that will break all the covalent bond in the depletion region. But here we are not able to achieve that critical voltage. Whatever we increase the applied voltage, when we goes on increasing the applied voltage, a time will come when the electrons will get sufficient amount of energy and they will collide with another covalent bond. It will break those covalent bond and those covalent bond result into another electron. These two another electron further gain energy from the applied voltage. Now they will collide with another covalent bond and they will result in 4 electron, and this process will known as avalanche mechanism or avalanche process, and this process result in a large amount of current flowing in this configuration. Clear? So this relation is very important. External electric field, this is the total D and the external electric field, and V is the applied voltage, and internal electric field built-in potential D and EI. So this is very important. Okay.